There are 6 features of a normal distribution that you need to know. The reason you need to know them is that it is partly you might get questions like this, where you need to use some of the features of a normal distribution to solve a problem, but also you are sometimes asked to justify your use of the normal distribution. So here is a situation, it is about some mice or whatever. Is it okay for us to use the normal distribution? Or explain why it's not okay to model this situation with a normal distribution. So what you would do in your head, you would go through these 6 things and say, well, are they or are they not true in this particular mouse-based scenario? And then you can say, yeah, they're, you don't have to necessarily check all 6, but that's what the examiner is going for. When they ask you to justify use of the normal distribution, they're saying, do you know that in order to model a situation with a normal distribution, these are the things that we would be looking for? So the first one is this. I was going to say it models continuous variables, but I think I'm just going to have that not as a feature of a normal distribution. It's just that normal distribution is used to model situations in which your variable is continuous. So things like height, weight, length, volume, blah, 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 that sort of thing. Right, first thing, it is symmetric around the mean. Has to be symmetric. Okay, number 2, the mean is where the peak is, and that is also the mode, which is also the median. So the fact that the mean equals the median means that the data has no skew. You don't need to particularly use that technical word skew, but you do need to know that the mean and median are identical in a normal distribution. And right, next one, the total area under the curve is 1. That's important because it's a probability curve. So in a discrete sense, probabilities add up to 1. And in a continuous setting, the area under the curve is the probability, and so that totals 1. It is a bell-shaped curve. Does it look like, do you know what? I've never even questioned what sort of bell that looks like. Is that what bells look like? I don't even know. Anyway, it's a bell-shaped curve and it has asymptotes at each side. Now in real life, your real actual mouse scenario, it wouldn't be asymptotic because really, you could say, there's no biggest weight of mouse, but on the other hand, if you imagine you've got a mouse which is a particular weight, if you just put a tiny extra atom on, then it will weigh a bit more. So it theoretically goes out and out and out. Now on the left hand side it doesn't, because the mouse can't weigh less than 0, but this, don't forget, is a model. This is not real life. The mice are real life. What we've got here is a model, and the model is asymptotic on both sides. So it's bell-shaped and asymptotic both sides. Number 5. This is an important one. It's got inflection points. Now, an inflection point is where a curve changes from concave to convex or vice versa. So if you have a look at the top of this curve, then it is concave. All of the chords would be underneath. And then by the time we get down here, it's convex. So somewhere between there and there and there and there, it's changed from convex to concave and then from concave back to convex. Now, where are those points of inflection? This is really important. The points of inflection are 1 standard deviation out from the mean. So it's the mean, forwards or backwards, the standard deviation. So from the centre point out a standard deviation, that's where you're going to find the inflection points. Now, number 6, let's just do this so then a bit clearer to read. Number 6 has got 3 bits of information in it, so you could call it 3 bits if you want, but really it's just giving you an indication of if something is distributed normally, then this is what it will be like. If you go 1 standard deviation out, so you go to the inflection points, so this is forward a standard deviation and backwards a standard deviation from the mean, then that area there will always be ish 68%. Won't be bang on, because real life is, no, it would be. It would be 68%. Always between the two. No, it will be. Ignore me. It will be 68%. but I don't know what it is to more decimal places. Right, what if we go out further? What if we go out 2 standard deviations forwards and 2 standard deviations backwards? Then this area here is going to be about 95%. Now, if you go out 3 standard deviations from the mean, then you basically end up with everything. So it's about 99.7% of the data, but you can think of it as all of it. So all-ish, I'll put 99.7% data is within 3 standard deviations of the mean. So this is something you could check. If you've got some data, then you could work out the mean, you could work out the standard deviation, you could get the mean and go forward 3 standard deviations and back 3 standard deviations to get a range, and then you could see whether or not all of the data or almost all of the data was within that range. And if it isn't, if there's other stuff out here, then that indicates that a normal distribution will not be a suitable model. Right, let's try using some of these things on these problems. Right, first one. As always, the picture is the key to success in a normal distribution question. So I'm going to draw a little picture. I don't know. Oh, I've gone at a bit of an angle there. Sorry about that. I'm going to fix that because that'll, if it annoys me, it'll probably annoy you as well. And that's not ideal. We don't want to be annoyed when we're trying to do a normal distribution question. There we go. That's, oh, look, now it's, oh my goodness. There. It's like just about acceptable, I think, as a normal distribution. Right, I don't know what the mean is. It'll be in the middle, but I don't know what the mean is. The variance is 25. This number here is the variance. That's that second number. And that is a measure of how spread out it is, the distribution. So this one's got like a small variance, quite squished up and high. This one, it's more spread out. It's got a bigger variance, a bigger standard deviation. So the standard deviation is 5. Right, 70 grams. 97.5% of the mice weigh less than 70 grams. So this here is 97.5%. Boop, in there, okay? Now, how are we going to use that? Because it's not anything that I told you. It's symmetric, yes, fine. The peak is at the mean, yes, fine. Total area is 1. I suppose, okay, I could use total area is 1 to work out that this bit here is 2.5%. It's a bell-shaped curve, yes. It's asymptotic, yes. It's got points of inflection there. I mean, I drew, actually, do you know what? I didn't draw it very well, did I? It's not very symmetric. But all of these things here were about in between, not to the left. But if this is 2.5%, then if I take another 2.5% off the left-hand side, and I go, that's 70, that's 2.5% there, and that's 2.5% there, then this is going to be 95% because I've taken another 2.5% off. So this here is going to be 95%. Now, if that is 95%, then that means that I have gone out 2 standard deviations from the mean to get there. So the mean plus 2 standard deviations is 70. 2 standard deviations forward. And if I went 2 standard deviations back, I'd get there. Now, I know the standard deviation is 5. So mu add 10 is 70, and we found the mean. The mean is 60 grams. Easy peasy once you've drawn the picture. Right, let's have a look at this one. State the value of the mean height. We need to know that the peak is at the mean. And so let's have a look. This would be on graph paper ideally, but there we go, 36. So the mean is 36. 36 centimetres. Okay, and that's also the median, because in a normal distribution, the mean and the median are the same. Right, how are we going to estimate the standard deviation? This is, I mean, like, what? I haven't even got any information at all. This is where the inflection points come in. Now, what we need to do, this is difficult. It's not going to be obvious at all. And yes, there is, it's not an exact science, but you're going to try to find the point on the curve where it changes from being concave on this side to convex. I think it's about there, and it will be symmetric, and that means that if we go down and have a look, these are the inflection points. What do we get? So inflection there and an inflection point there. But the inflection points on a normal distribution are always, always, always 1 standard deviation out. So there's the mean. If I go forward a standard deviation and back a standard deviation, then I will end up at those inflection points. So the first, what have I got here? 34 is the mean, which is 36, minus 1 standard deviation. So that means a standard deviation is 2 centimetres. And what about the other side? Yep, it's almost bang on exactly the same, isn't it? So we could have or 36 plus 1 standard deviation is the other inflection point. So again, obviously we're going to get the same thing. So yeah, learn these 6 and apply them to a situation to see whether or not a normal distribution is appropriate, or if it is, you can use this sort of information to solve problems.